Alright, in this video we're going to look at some of the rules of differentiation, and that's because if we always had to rely on the definition of the derivative to find slopes of tangent lines, then it would be really tedious and we wouldn't want to do it and calculus wouldn't be enjoyable. So fortunately there are these rules that we can use which all stem from the definition, and the proofs are all based on the definition. I probably won't do the proofs here, maybe in another video I will, but just want to give you the rules and then a few examples of how you'd apply them. So I'm going to shrink this down, and we'll take a look at them one by one. So first, let's take a look at the power rule. So the power rule, and for instance, let's just start with a simple example. So, and we'll connect it to the geometry we know. So the derivative of x to the 1, according to the power rule here, it says that that's equal to 1 times x to the 0, which is 1 times 1, which is 1. And graphically that should make sense because the graph of y equals x is just a diagonal line whose slope is always 1. So, so that makes sense. I'm sure in previous exercises in your course you've done examples of using the x plus h definition for functions that are quadratics, so I'm sure you've seen that the derivative, for instance, of x squared, if you use the definition, gives you 2x, and the derivative of x cubed is going to be 3x squared. I guess I'll put a 1 there to be technically correct. So that's the power rule. The general proof, if you wanted to prove it, there's a couple ways to prove it, but one would involve the binomial theorem, so I'm just going to note that here. Proof. You just use the definition of the derivative and then apply the binomial theorem. So if you're interested in playing around with that, you can. Okay, so that's the power rule. Now let's take a look at the constant rule. So let's go, I'm going to block this off. Let's go do the constant rule. So the constant rule says, sort of two pieces to it. It would say that the derivative of a constant is equal to 0, and this shouldn't be a surprise because the line y equals c is a horizontal line whose slope is always 0. So that makes sense. The other part of the constant rule that I lumped in here has to do with how constants can be factored out or moved outside of the derivative. And so as an example, if you think of, let's take the derivative of 2 times f of x. According to the constant rule, this is just 2 times the derivative of f of x. And so why does this, intuitively, why does this make sense? Well, it's because when you take 2 times a function, you're multiplying, you're stretching, so multiplying by 2 stretches stretches the function vertically by a factor of 2. So when you stretch a function vertically by a factor of 2, that implies that all your, if you think of slope language, all the rises double, right? Rises double, and your runs stay the same. Which means that your slope doubles. All right, so there's just one example, just to give you some sense of why that rule works. But it's easy to apply and convenient, even if you don't write it out as rigorously as I did there. And then the last useful rule has to do with sum and differences of differentiable functions. What we would want to have happen is exactly what does happen. So let's just use an example of taking g of x to be x cubed over 3 plus x squared over 2 plus x. And let's use Leibniz notation. I'm going to say the derivative, dg dx. Well, according to the sum and difference rule, we can just take the derivative of each term separately. And even if you're not as rigorous when you actually do these problems out, I'm just doing it out once to show you how it works. Now we can just apply the power rule 3 separate times. So this would be 3x squared over 3 plus 2x over 2 plus 1, x to the 0. And that, of course, is just going to be x squared plus x plus 1. All right, so here's a brief video on some useful differentiation rules, which you'll probably start using from now on instead of the definition whenever possible, just to make the problems less tedious. All right, following some basic rules on differentiation, it makes sense to start talking about how you can apply them. And we'll start with looking at a polynomial and trying to find where it has horizontal tangents. So we've got a cubic here. It should have horizontal tangents, most likely, because it's got some turning points. So let's just note that a horizontal tangent, that's going to occur where the derivative is 0. So horizontal tangents occur where y prime is equal to 0. So let's find y prime and then set it equal to 0. So y prime, and now here's where we use the power rule. We'll go term by, and the sum and difference rule. We'll use the go term by term. The derivative of x cubed is 3x squared. The derivative of negative 2x squared is a negative 4x. And the derivative of x is 1. And the derivative of 1 is 0. So there's our derivative, and if we set that equal to 0 to find the x values that make this expression true, we see we've got a quadratic. It looks like this will factor, as if I rigged it that way, which I most certainly did. So it factors into 3x minus 1, x minus 1, and that means that we have horizontal tangents at a third and at 1. So we have horizontal tangents at x equals a third and at x equals 1. Now, if I want the points of tangency or the equation of the tangent line, I'm going to have to evaluate the function at these points. So I'm going to use this notation, y of a third. Now I'm just going to use my calculator here because it's too tedious to plug that in and do it out by hand. It's about equal to 1.148, and y of 1, which we could probably do out by hand, is actually 1. So we can say our points of tangency are a third, comma 1.148, and at 1, comma 1. If I wanted the equations of the tangent lines, then it would just be, well, it's a horizontal line, so it's just gonna have an equation y equals a number, and it's gonna be y equals these y coordinates. So our equations of our tangent lines would be y equals 1.148 and y equals 1. Okay, so there's a simple example, which mainly I did to apply the rules of differentiation, which are going to make problems like these much easier as opposed to going back to the definitions over and over. On the next page, I just have this this function's graph and those points of tangency, so you can confirm what we found out using calculus with an actual graph. And so here we see that our calculus was working for us. We found the two locations where we have horizontal tangents. So it's always good to check using a graph just to confirm that your calculus is doing the work correctly for you.